Mm, Okay.
Hi, good afternoon, everyone. Welcome back to the new episode of the Machine Learning Systems Singapore Seminar. And today, we are very fortunate to invite Qiaolin to be our speaker. Qiaolin is currently a research associate in NTUS lab, and she plans to start her PhD candidature in August under the supervision of NTU professor Zhang Tianwei. Her research focuses on the optimization of large model training systems. Okay, Qiaolin, you have the floor now.
Hi, I'm Chaoling, and thanks Hao for his introduction. And I'm honored to receive the invitation to come here and share you with about the AMSP. And I'm also very excited to discuss the topic of LLM training with you. Today, I'm going to share ASP, superscaling LLM training while advanced model states partitioning. And if you have any question, please feel free to discuss with me after my presentation. First, I'd like to talk about the background of superscaling LM training. Well, as we all know, the previous practice was that in order to have a better performance of a model, we would, when the size of model increase, both the amount of my data and the number of GPUs corresponding to it have to both grow. And as is shown in the graph, the x-axis is the years from 2080s to 2022, and the y to the July 2023, and the y-axis is the number of tokens needed to train a model. Each point in the graph represents the models and its corresponding size. In the observations between 2080s to 2022, we notice an exponentially increase in the size of model parameters and the number of tokens during training from 1.3 B tokens for the GPT-1 models in 2018 to 7B to 400 B tokens for the GLM models in 2022. And at the same time, the performance of the resulting LLMs is steadily increasing. And this trend is consistent with OpenAI's scaling laws, which states that increase in the model size and the data volumes and the GPU resources used for training will lead to a gradual increase in the performance of LLMs. However, the situation changed after 2022 when DeepMind proposed a new scaling law, the named superscaling law. This law asserts that the increase in the data volumes takes precedence over the increase in the model parameter during training. This evolution of scaling strategy emphasized the importance of the data sets and the quality when training large language model. On the ways, you can see that the number of tokens used for the model size around 7 billions grows exponentially from 2020, 2022 to July 2023. And in the framework of superscaling law, model size are typically small with parameter of 7B, 13 bits and 13 billions model size. However, the amount of tokens increase dramatically, usually reach the 2 TB level. Yeah, and to efficiently process the data of these magnitudes, thousands of GPUs are typically deployed. And the original designs of ASP stems from our practical business need to train a llama model of size 7 billion parameter using 2T tokens in 1 month using a cluster containing thousands of GPUs. These requirements reflect two features. The first one is due to the model size, which exceeds the processing capacities of a single 80 GPUs. And we need to partition the models to reduce the memory burdens on a single GPU. And the secondly, is that although we utilize thousands of GPU to process a large number of tokens, the number of tokens processed in each batch is usually limited to 4 millions in order to ensure that the training process achieve good convergences in real world. This means that despite the large number of GPUs, the amount of data actually processed per GPUs, the amount of data processed per GPUs is relatively small. So the limitation of the global batch size results in the training of the 7 billion model being extremely sensitive to the latency, especially when dealing with the communication overheads introduced by the model partitioning mentioned in the first point we mentioned. So while we attempt to improve the efficiency, we use the advanced training system like DeepSpeed Zero and NVIDIA Matrix. However, the actual MFU is not good, was found to be only 32% and 17% for the Matrix and DeepSpeed. Yeah, and we identified two major performance bottlenecks. And for the DeepSpeed Zero, when we adopt the 0-1 mechanism, distributed optimizer across thousands of GPUs, the corresponding communication overheads takes up nearly half of training time. And for the Matrix, the communication introduced in the critical paths also consume about a quarter of training time when using the tensor parallelism. Well, the main idea of AMSP is to solve the scalability problem of scaling up the training of medium-sized models, 7B or 7 billion models or 13 billion parameter models on thousands of GPUs by redundantly storing model states and independently assigning the three member of model state parameter gradients and optimizer states. And first, we first talk about the redundant partitioning. We found that the possible reason for the poor training scalability is the limited scalability of the communication operator itself. We run a benchmark of nickel on 16.4 and 512 800 GPUs with NVLink within nodes and infinite bands between nodes, and the results are shown in the figure. The x-axis of this figure is the message size, and the y-axis is the effective bandwidth. We can see that the orange and blue and green lines represent the effective bandwidth of three common collectives algorithm on a different message size. And take the orange lines reduce scatter as an example. When the message size is 32, the effective bandwidth at 512 GPUs is much lower than that of 16.4 GPUs, which indicates the poor scalability of the communication, scalability of the reduced scatter operator itself. So this inspires us to reduce the communication overhead by redundantly storing all model states in a subset smaller than the word size. For example, when we have 512 GPUs for training, in order to avoid the decrease of effective bandwidth under 512 GPUs, we limit the communication scope to 34 GPUs, in which case A copies of model states are redundantly stored in 512 GPUs. and the communication scope of each copy is 64. And another idea of AMSP is to independently assign the three members of model states PGMOS. The idea of independent allocation stems from the important observation. When using Adams optimizer, three elements in the model states, the parameter P, the gradient G, and the optimizer states OS, differ significantly in terms of their memory and communication requirements. In the scenario where the mixed precision training is used, the optimizer has a memory footprint 6 times larger than that of P and G. And further, the communication requirements, we notice that when we slice P, G, and OS with the same granularities, the optimizer only needs to perform broadcast communication once in each training steps. In contrast, the number of communication between the parameter P and the gradient G is related to the number of gradient accumulation step. We call N. Yeah. So specifically, the parameter P requires 2 times N altogether operation in the forward and backward propagation of each training step, while the gradient trigger only one reduced scatter operation in the backward propagation. And this observation inspires us to allocate P, G, and OS independently, allowing for more flexible management and of memory allocation and communication costs. And let's move to the system design. Okay, well, this is the architecture and the workflow of AMSP system. First, a unified search space is created for the model states based on the model size entered by the program and the GPU computation resource. Subsequently, ASP use its scale-aware partitioner to generate the optimal combination of model state partitions, ensuring that GPU memory constraints are adhered and while minimize the communication overhead. And there are two key elements in these partitioners. The first one is the data dependence-based strategies, which is designed to pre-filter our strategy that might result in significant data transfer costs. And the second one is the cost model constructed for the communication and the GPU memory associated with the combined strategy. And once this model built, we use ILP algorithm to determine the optimal partition strategy. And after finalizing the strategy, we design an integration of general communication strategy to further optimization. And first, we talk about the unified search space. And I think one of the core innovation of AMSP is the introduction of the concept of unified search space, which provide a new framework for model state partitioning that can be adapted to multiple redundant strategies. And these redundant strategies, including the whole replicate and full partition and the partial partition named inter-partition and inter-replicate strategies. And it also allows for dynamic partitioning of model states so that the partition of P, G, and OS can be dynamically adapted as needed. And after that, ASP use a partitioner in this space to generate the optimal combination of model states partitions. And we begin by introduce the first components in the partitioner, the data dependence rules. While during training, a base sequence is observed. The parameters are used to compute their corresponding gradient. Subsequently, these gradients are used to update the optimizer states, and the updated optimizer states will replace the training parameter in the next step. This process highlights the fact that there is a strict data dependency between these three main members of GP of the model states, PGMOS. And this leads to complexities and the potential inconsistencies when the members use different partitioning state strategies. And the additional data movement may be required to maintain the accuracy and the integrity of the result, which will increase the communication overhead. And as an example, suppose that the P parameter of the model states model choose the full partition strategy. I mean, they will be distributed across all GPUs. And in contrast, the gradient choose the full replicas strategy, while a full copy is kept at each GPUs. And in this configuration, the gradient from each parameter partition must be aggregated each time the gradients are partitioned. This aggregation is typically achieved through the all-gather operation within a word-size communication group, which will introduce additional communication overhead and very expensive. So in order to reduce this additional data transfer, we have developed a set of combination rules based on data dependencies. That is, when the OS partition dimension is larger than that of G and P's partition dimension, and the G's partition strategy dimensionally is larger than that of P partition dimension. And following this pattern, ensure that any data dependence in the upstream has full access to its allocation of the downstream data, thus facilitating the computation of the gradient and the updating of optimizer. And the second components in partitioner is the memory and communication cost model for combining P, G, and OS policies. And as we mentioned earlier, the optimizer typically takes up 6 times more memory than P and G, and the overall memory of the cost of memory of the model states can be expressed as the sum of the memory footprint of P, G, and OS respectively. And their respective memory footprint on GPUs are related to the number of slides they choose. While the communication cost of PGMOS can be simplified to the product of their communication volumes and the communication counts and the cross-node communication volumes. After that, we can automatically determine the optimal partitioning strategy by minimizing the communication costs under the memory constraints. Well, and compare with the deep space zeros, manually selection of 0, 1, 2, and 3. AMSP can automatically find the strategy for different combination of PG OS slice in a larger space. And when we finalizing this strategy, we further design the hierarchical communication strategy to reduce the internodes communication and ensure the accurate data. For the parameter and gradient that satisfy the data dependencies. their corresponding communication, P is 2 times M altogether and G is N reduced scatter. We can abstract a hierarchical three-stage communication method, denoted as internodes, then internodes, and finally internal to achieve the effects of communication aggregation. This figure above visualizes the three-stage algorithm which can achieve the effect of communication aggregation. Yeah. Well, let's move to the implementation and evaluation. Well, we implement ASP based on the Microsoft Magnetron DSP. And the main core code developed from the DeepSpeed 0.9 version. And we evaluate ASP on training Llama 7 bits, 13 bits, and 13 bits model parameters at thousands of GPUs with global batch size equal to 4 millions and sequence length of 2048. And we use MFU as an evaluation metric. We can see that ASP perform well in both 7 billions and 13 billions training. And while at 13 billions ASP performance is similar to the Magnetron, which we believe which we think that is due to the fact that the number of parameters in Llama's 30 billions is larger, which leads to a rise in the amount of computation. And at this point, the ratio of computation to the communication rise. So the communication is no longer the bottlenecks. This is where the advantage of NSP is no longer apparent. And here is the details of the baseline configuration. And thanks for the listening. Yeah.
Okay, thank you, Qiaolin, for the insightful presentation. We now open the floor to questions. If everyone has a question, please raise your hand and unmute yourself. Okay, let me ask two questions first. I see that you are compiling 7B and 13B to 30B models here. Have you tried to compare with the larger model?
I can't hear you. Sorry, I missed
Sorry.
that backward.
Okay, I repeat again. I see that you are comparing 7B model to 30B model. Have you tried to compare the larger models?
No, because we do know that the ASP performs well only in 7Bs or 13B model parameter size. And it is only in this scenario that it performs well. So we don't think will perform well than Magnetron when we have a larger model size.
Okay. I think you compare it with the Zero and Magnetron. Have you considered to compare the performance with PyTorch FSDP?
Yes, I know the FSTP. There is a difference from FSTP with Zero. It has a hybrid parameter when we use FSTP. But I understand the parameters. It actually gives the final results that the PGMOS maybe in a mode where they are all divided in a single nodes. So we prepared the same effects of another system like mix. So in some ways we compare FSDP.
Huang Ting, please yourself if you do not have a question. Okay. So is there any further question? Okay, we will bring this section to a close. Thank you everyone for your participation. Happy Chinese New Year. Thank you everyone. Bye.
Thank you. Bye.